Okay, in the previous video we have considered an example of a binary statistical classification problem, and in that case we have calculated the confusion matrix by choosing the cutoff, if you remember, here at a value of less than 10 flight experiences, and then we have also derived the J statistics index. That is, after we have calculated the sensitivity and the specificity, or let's say the true positive rate and the true negative rate, and then the fallout follows from the specificity, the false positive rate. Then we saw that this index, which is given by the difference between the true positive rate and the false positive rate, as a means basically the difference between the benefits and the costs. Now, in the following exercise, we want to explore this trade-off between benefits and costs. So this trade-off between true positive rate and false positive rate more systematically. And then for that we introduce the so-called ROC curve. So basically in the ROC analysis you investigate the trade-off between true positive rate and false positive rate, or let's say between the sensitivity and the fallout. So the basic idea of the ROC curve is to make a plot of the true positive rate on the y-axis against the false positive rate on the x-axis at different values of the cutoff. Or in other words, if you remember that in the concept of machine learning, the sensitivity is also called recall of probability of detection. Basically, we want to study the probability of detection, the trade-off between the probability of detection and the probability of false alarm, which is corresponds to the false positive rate. So basically what we have to do is for different values of the cutoff make a prediction for this, then a point in this diagram by calculating, so for each value of the cutoff, again the confusion metric and then the true positive rate and the false positive rate. And the final function that you obtain then illustrates the trade-off between true positive benefits and false positive costs. So basically what we have to do is to redo this calculation, just choosing not only one value of the cutoff, but for all the possibilities. So taking the cutoff, for example, at flight experience less than 2, flight experience less than 4, and so on, up to flight experiences less than 20. So one possible way to proceed is to open our Excel calculation of the previous video, and then to repeat the calculation basically again and again, just for different values of the cutoff, and then to make a plot of the quantities, basically false positive rate and true positive rate. Now this is one possibility that you have, but in this video we want to try to find out a better solution, let's say a faster solution than just to repeat again this calculation and to derive one by one the points. So for that, let's open again this file with the data given of the sample investigation, about 186 clients, and let's proceed in this way. So this is also suggested in the text of the exercise, where it's written try to calculate automatically the columns for true positive rate and false positive rate from the 3 columns in the test table above here. And a hint is given basically try to use the cumulative function in the columns don't buy and buy. So we want to take this hint and to develop this into a fast solution of this problem, at least faster than to redo again and again the calculation for the confusion matrix and TPR and FPR of the previous exercise. So let's start from here. I take over the text of the exercise and then I give you basically what my solution is. It is possible that there are other possible ways to get a fast solution. That's up to you. I mean, I just give you what my solution is. So basically what I do, I create here a column where I put the value with the classes, the number of flight experiences, and I take over also the two columns with buy and don't buy here, and I call them differently, so because I may want to make connection with the theory of confusion matrix, so I call this failure, and for buy success, because no, this is the correspondence. Then here, as is suggested, I create two columns with the cumulative basically values of these two columns. So I call it this cumulative failure, and here cumulative success. Yes, it's written wrong. Okay, and then I calculate these two columns. Basically here in the first I get the same, and then in the second I put the previous one plus the next one here, and then I take it down up to here, and the total must be 527. The same I do here for the column with buy, so this is equal, and then I take the first one, okay, and here in the second I take this plus the next one, and then I go it down. In this way I get the cumulative value of this column up to the end, and here I must get 279. Okay, this was now we will see in a moment why this can be helpful, because what I want to do is I want to create here to have somehow as a function of the variable flight experience the TPR, the TNR and the FPR, basically especially the TPR, the true positive rate and the false positive rate. So I write here true positive rate here, true negative rate, the specificity, and then more importantly the false positive rate, and to have this basically as a function of the cutoff. So this this column I want to now to call it cutoff. So I will choose first the cutoff at 2, then at 4, then at 6, and so on up to 20. And then I want to create here the columns for TPR and FPR and then to plot them. Okay, so why is the cumulative, these cumulative columns that they are useful? So first of all, consider that in this case that we are varying the cutoff, so the prediction will be different. I mean, these values of the predicted and predicted pi for the different value of the cutoff, they will be different, but the observed failures, the observed don't buy and the observed buy, they will be they are given here. So for this number, the total observed negative must be 527, and or better to fix this way, equal to this, and the total observed, the real by success, they are equal to 279. Then, okay, suppose that I have set the cutoff to 2, okay, then it means, what does this mean? It means that, for example, if I want the true positive rate, then I have to take the true positive divided the total observed real positives. But if the cutoff is 2, who are the true positive? Basically, you see that only this 3 here, they will get a prediction equal to 0, basically. So don't buy, but they actually buy. So the true positive are all the other. So if I want the true positive rate, basically I have to fill here this is equal, and then I take everybody, so 279, and I have to fix this because this will be always the same, minus, in the case of cutoff equal to 2, only these are the 3 are the false negatives. Okay, and then I divide by the all observed positive, and they are this again 279, and this must be also constant. Okay, so enter. So you see this value gives me the true positive rate in the case of the cutoff at 2. And let's also to approximate this with only 3 decimals. Okay, we can let it maybe 4. Okay, so this was the true positive rate. Now, since the argument depends only on this value of 2 here, then I can extrapolate this to, or extend this to along all the column. And so I get the true positive rate for all different values of the cutoff. Okay, for example, just wait, I see that when I extrapolate this result, I should not use this column with success, but actually, as I say, the cumulative column. And so basically I have to correct this here. I not use H3, but J2, sorry. Okay, and then I have to extend this below. Okay, and then you see I can also check, for example, if that I look at the value of cutoff of 10, then here I get 0.7921, and this must be in agreement with what we got in the previous exercise. Yes, 0.792. And it's indeed the same, 792. Okay, so this because this we already calculated for the cutoff of 10 in the previous exercise. Okay, then in this way I calculated the true positive rate. Then now I'm going to calculate true negative rate. Okay, let's still consider the case of the cutoff is at 2. Okay, so if you see, if the cutoff is at 2, the only true negative, it will be predicted failure and actually don't buy, and they actually will not buy, are these two 34. Okay, it's better. Again, I made the same mistake. I have to look at this column. All other people, basically, they will be false positive because they will be predicted to buy one, but actually they don't buy. So basically in this column, you see, I can take here this, equal to, then I take 34, and then to divide by the total amount of people which is not buying. So this 527, and this also must be constant everywhere. Okay, and then of course I can move this downwards until I get basically all the possibility for the true negative rate for the different values of the cutoff. Again, we can check our calculation. For example, if we look at the case of the cutoff at 10, so we get for the true negative rate is 0.784, and if I look at what we had, it was indeed this one, 0.784. So that's correct. You see, I reproduce the old result for the case of the cutoff at 10. You always try to check with what you know, your calculations. Now, we know that by definition, the false positive rate is just equal to 1 minus the true negative rate, because it's when you work on this column, right? So the recall is equal to 1 minus, and then I can plug this value, and then to move this also downwards. Okay, then everywhere is better to have less decimals. That's 4 are enough, and here as well. So here also I consider less decimal after the comma. Okay. So we see that by using these two columns with the cumulative don't buy and buy, we were able to calculate at one shot, let's say for each different value of the cutoff, immediately the true positive rate, true negative rate, and false positive rate, without repeating the calculation of the confusion matrix again and again. Okay, now basically I have the two columns for the different values as a function of the cutoff of false positive rate and true positive rate, and I can proceed to make the plot. You know, if I plot on the x-axis the false positive rate and on the y-axis the true positive rate, then I get the ROC curve. Okay, so I choose these two columns, this one and this one, and then I say insert, and then I go for this scatter plot with some line. But of course, you see at the present moment I have the x and the y axis inverted, because I have it, let's say on the x axis I have the true positive rate, and so I want to exchange these two. So I can do this, for example, there are many ways. Select data, and then I say edit, and you see then I can change here the x value. I take this column, okay, and for the I values I take the true positive rate column, okay, and so this is, you see, is the ROC curve which I get. I give also a title here. Sorry, this. So you see that for some reason I have some very strange x and y scale. So I check this, what is going wrong here. So I go to format axis, then I go to number here, type, I want indeed this one. Format. Okay. I have category custom here. This sounds very strange. So I just take the option general, and you see I get from 0 to just usual numbers, and I say I do the same also on the y-axis. So I go here to y-axis, and here again it is custom. I don't like it. I take it general. Okay, moreover, you see that the maximum is I know that the ROC curve goes up to 1, so I take here 1 as maximum. And also for the x value, I thought it was no, okay, this was okay. So you see now it is better because it's really between the 0 and 1 both on the x and the y scale. Okay, so this is the ROC curve which was asked in this question 1. And actually, if we want, we can add here on the x axis the title of the axis is the false positive rate, on the y-axis the true positive rate. But okay, let's now before we are going to question 2 to check what is the basic idea of the ROC curve. You know that for each point of the cutoff we have calculated one point in this XY diagram, and that together they form the ROC curve. So if I want to understand what I have done, I take over this diagram to the theory slide, and then we check what are the usual features of the ROC curve. So we see that basically each point, then for each value of the cutoff, I have a classifier. And as you see, the best possible classifier will be basically this point here. This is the perfect classifier because it means that you have 100% sensitive. You basically have no false negatives. And this is easy to see because a point here, the perfect classifier, it means that the false positive rate is equal to 0 and the true and the the true positive rate is equal to 1. So you see that if the true positive rate is equal to 1, if we look here, it means that the false negative are actually 0. But we must have also 100% specificity. So at this point we have no false positive, because as we can see, if the false positive is 0, it means that here basically the false positive must be 0, because the false positive rate is calculated along this column. Okay, so basically this is why the this point 0, 1 is the perfect classifier. Then we have the other limit, and the other limit is when basically your decision is based on chance, and that this is given by the line of no discrimination, which is basically the diagonal line, when you have the true positive rate and the false positive rate are the same. And this is basically when you decide, you make your decision, you make your test, just for example flipping a coin, okay, as we have seen in the other exercise. So basically, because a test based on a coin flip will predict buy and not buy with the same proportion for let's say people which are going to buy or as well as are not buying, then as far as the sample increases, then basically this line should approach the diagonal line. Okay, then what we get is something in between, and basically we have that the more the curve moves towards this direction, to the perfect classify, the better is your result. So you see that our result is definitely not very bad. And so with this in mind, we can move to the next question, which is basically the calculation of the Uden J index. And this is very easy because we have already the columns here ready. Just use the definition. Uden J, this is equal to, according to the definition, of the difference between the true positive rate minus the false positive rate. Okay, and here as well I can extend the calculation. And you see I can also check that this value for 10, 0.579 must be in agreement with the calculation that we got for the J index in the other exercise, 576. Let's check. Yes, 5.7 approximately with 6. Okay, so this was the J index, and we see also that indeed with the choice of the cutoff up 10, then that Uden index is as a maximum. So this was basically the best informed decision. So we see that you see that in this case our first choice for the cutoff, which was based on some common sense inspection of this table, basically is in agreement with the optimum find through the ROC curve, just looking at all the indices for all the possible cutoffs. Okay, then in the next question we are asked to give a graphical representation of the J index on the ROC diagram. Okay, if you want to understand it, okay, we know that the J index, it is just the difference between the true positive rate and the false positive rate for each value of the cutoff. And if you remember the theory of the last time, we say that basically a zero value for the J index represent the level of chance performance. So when you take the decision just flipping a coin. So basically, I think if we want to understand what is in this diagram, the this J value, we have also to plot the line of basically random decision, so the diagonal line in the ROC curve. Okay, let's do that. So if we want to plot a diagonal line between 0 and 1, we can add here some coordinates, so equal to this minus 0.1, and then this up to 0, and here as well equal to 1, and then equal to 1 minus 0.1, and then to extrapolate this. And then if I take a plot of these two lines here, wait, I select here and then insert, then I make again scatter plot, and then I merge these two diagrams, copy, paste, oh sorry, wait a second, so just try again. Here, copy and paste. You see, okay, then I have the merge the two diagrams. This I can also remove it. Okay, so we have then our ROC curve together with the diagonal line. And now basically I want to understand for each value of the cutoff what is the meaning on this diagram of the index j. Now if we consider the coordinate, okay, take for example one value, this value of 10 for the cutoff, then we know that we are in that case at this point. Okay, this is the classifier that we get. And let's write down what are the coordinates here for the value of the cutoff of these points. Basically, we have that this point as coordinate false, as a coordinates false positive rate, comma, true positive rate. Okay, they are the coordinate of this point for the cutoff. Of course, the false positive rate and true positive rate for this value of the cutoff. While the point on the diagonal here, which lies precisely below, it has coordinates which are false positive rate, and in this case the I coordinate is exactly the same, false positive rate. So we see that this distance basically it is just equal to the true positive rate minus the false positive rate, but this is just the j index. So we see that the j index, which in this case it was given by this value of 0.576, it is given by the distance of the point on the ROC curve to the diagonal line. Okay, this is the graphical interpretation of the j index, and of course this is true for all the points. So basically we have derived this for this value of 10, but then for this other point then you will have this j, okay, or this j, or this j, and here also is difficult to draw, but I think you understand. Okay, is the distance of each point from the diagonal line, because they are the reference of let's say of no information at all when you take the decision based on chance. And so we see that the ROC curve gives also basically visual description of visual access, I would say, to the knowledge of the cost-benefit trade-off for each value of the cutoff. But you see that on the other hand, you see that the j coefficient is something local, okay, that is given for some specific value of the cutoff. While we will also like to give an evaluation of the classifier as a whole, and for that we have another tool, which is basically the R area under the curve, as explained in the theory. Basically this area under the curve is a very useful tool, because we have said that the more, let's say, our diagram, our curve approaches the perfect classifier, so that means the larger is this surface, the better is our classifier. So if we calculate, and we know that in the case of the perfect classifier, this will correspond to an area of 1, because I have a square here 1 by 1. So as far as this value, this surface approaches the value of 1, the more it approaches the value of 1, the better is our classifier. And this, we have a curve which is not a continuous curve. We have a curve which is basically is given by some straight line which connects the different points, different value of the cutoff. So we can try to calculate this area with some approximation. And the kind of approximation is indicated in the text of the question. Basically, it is trapezoidal approximation. It means to use the same formula that we have used for the calculation of the area in the case of the Lorentz curve. Sorry, I go back. So basically this formula, okay, which where this formula comes from, I explained there, so look at that video. And so where of course the x variable in our case is the FPR, the false positive rate, and the y variable is the true positive rate on the y-axis. So what we want to do now is to implement this formula. In order to do that, I take the formula over into my Excel file, and we proceed implementing this formula as we did in the calculation of the Gini coefficient for the Lorentz curve. So I want to sum here from k equal to 1 up to n. So n will be the last, k equal to 1 will be basically this line. So this is the false positive rate is the x variable. This is the true positive rate is the y variable. So I add here, it's better to add here also 1 because the line must be finished there. Okay, and then you see I have a product of k minus k1, so I can take here, I can make immediately in this column the all these terms of the summation. So you see I can get here, for example, equal between parentheses, then I take x equal to k. This is the last term of the sum. So in this case is the x variable, so it is 1, and then I have minus the k minus 1, this one, and then times, and then I have now to take the y variables. The y variables are on this column here. It was the TPR, so I get in this case 1 minus, and then yk minus 1 is this one. Okay, and you see that there is an external factor 1/2, so I can also divide all the terms. If I take this 0.5 inside, then I can immediately put here, divide everything by 2. Okay, enter. This will be the first. Then I can extend this down to the last one, with exception of because the one before the last will be always 0 because I have the difference. And then if I sum up this number, then I should get the total area. Wait a second, I make a check if I have done correctly. Wait a second, I use minus now in the second in the y, then I have to use plus here because in the formula is plus. Okay, then I do it again, then I take this down. Okay, and then if I sum up this column equal, okay, then I can do it alt sum, alt equal, enter. Then I get this value, which is better to approximate only with 3, or let's say 2 decimals because it's a coefficient. Okay, I get 0.85. Definitely we see that this value of 0.85 is larger than 0.5, which is the level of chance. This is when you take a not informed decision, and I think it can be considered a reasonable high value. There is a literature about that you can explore and you can search. Okay, so in conclusion, you see that ROC analysis provides basically tool to evaluate your testing method of testing model before you are actually introducing a cutoff, so before making assumptions about the class distribution of the cost context. For this reason, ROC analysis is really related to the cost-benefit analysis that you and the problem of decision making. That's the reason why this method is increasingly used in machine learning. We have not done machine learning, just this is a tool that is used in the problem of binary classification, which is a problem which occurs in machine learning and data mining research. Final remark about the name. Now the ROC curve is called in this way because it's called the relative operating characteristic curve, because it gives a comparison of two operating characteristics, namely the true positive rate and the false positive rate. If you read in the theory about also the historical origin during the Second World War of this method, then you will understand better this definition. Eventually, before concluding, I want to anticipate that you will find again at least some kind of analogous of ROC curve, but in principle you could also consider the ROC curve itself later on, when you will have studied in the theory, statistics theory, the theory of test, so testing an hypothesis. Then you will see that there is a parallel between the problem of the classification theory, which we have discussed in the previous 3-4 videos, and the problem of hypothesis testing. And then you will see that just naming things differently, basically the same stuff, okay, the same plot, it will become a plot of the power of a test, which I have not defined yet, as a function of the type 1 error. Okay, so we will call later on, in the context of test hypothesis theory, basically the sensitivity will become the power of a test, and the false positive rate, so basically the false positive, will be called type 1 error in the case of a decision problem. Okay, so basically we will find a nice connection of what we have learned here in the problem of binary classification with what you learn at the end of the statistic module, when you will use to learn the z-test method. Okay, thank you.